We're in section 9.6. We're going to talk about the ratio and the root test. So for the ratio test, advanced pre-calc. All right, so the ratio test. For the ratio test, we have, all we need is, I'm not going to write my indices, so we just have the sum and infinite series, a sub n, and this is a series with non-zero terms. So it can be alternating in sign, it can be positive, so we don't have a lot of restrictions here. We have several things that happen with the ratio test. Our series is going to converge absolutely. If the limit, all we have to do for the ratio test, this is nice, is find a limit. A sub n plus 1 over a sub n is less than 1. Our series is going to diverge if that limit is greater than 1. And if the limit equals 1, we have no conclusion. We have to try something else. So there's our test. So we just form this limit and decide, is it less than 1, greater than 1, or equal to 1? If it's equal to 1, then we have to do more work. So this is a nice test. When you can use this test, it's a very nice test. The ratio test, ratio test is nice for series that involve factorials and exponentials. So we'll take a look at a couple of examples, but the proof of the ratio test is nice because it involves geometric series, and it's very, very easy, very easy. So let's walk through why this property would guarantee that we have a convergent series. So, and we're not going to be very formal. So we're going to say that we have this limit as n approaches infinity. We know this is true of a sub n plus 1 over a sub n is some r, which is less than 1. So assume that that limit exists and it's less than 1. By the definition of a limit, we can pick some n so that we can have that when we get out past this value of n, that this ratio is less than some other quantity. So we're going to choose r. So 0 less than or equal to r, less than or equal to capital R, which is less than or equal to 1. So we're just choosing some r that we want this value to get close to. We can have some n So when I get past this value of n for my terms, a sub n plus 1 over a sub n is less than r for n greater than or equal to this value. So we can just pick some number that this ratio is less than. That's our definition of a limit. So we can write a sub n plus 1, absolute value, is less than a sub n r. And I can keep doing this process. My next term is going to be a sub n plus 2 is going to be less than a sub n plus 1r, which is less than a sub n r squared. And I can keep doing this process. So the next term, because this limit exists, we can say that a sub n plus 3 is less than a sub n plus 2r, which is less than a sub n plus 1 r squared, which is less than a sub n r cubed. Well, this geometric series, this series a sub n, absolute value of a sub n, r to the n converges. A sub n is just a number, and r sub n is our ratio. So this converges. So our original series is going to converge by direct comparison. So we can turn this we can think of this ratio as our kind of like our ratio for a geometric series, and if that's less than 1, that guarantees that our series converges. So that's why we have that condition, less than 1, greater than 1. If it equals 1, we don't know. Something else could happen. And it turns out when we talk about the root test, I won't go through this for the root test, but the root test, the proof for the root test is similar. The conditions are similar and the proof is similar. So this is the reason we have those conditions, less than 1, greater than 1, and equal to 1, is it's related to a geometric series. All right, let's look at an example using the ratio test. And then we'll talk about the root test. So we want to test for convergence. I had a student a couple of years ago say, Mr. Beamer, why do you always say we want to? I say we want to do this, we want to do that. He says, what if we don't want to? All right, so we want to test this series for convergence. The thing that tells me that we might want to use a ratio test rather than the alternating series test is this exponentials and factorials. I said the ratio test works well for series, can work well for series with exponentials and factorials. So we're going to use the ratio test. So we're going to look at the limit as n approaches infinity of, and we want a sub n plus 1 over a sub n. So what we're looking at here n approaches infinity of a sub n plus 1 is going to be 2 to the n plus 1 over n plus 1 factorial. And we're dividing by a sub n, so I'm just going to flip that over right away, over times n factorial over 2 to the n. And then we simplify this. This is limit, and this is why exponentials and factorials work so well this way. What's 2 to the n plus 1 divided by 2 to the n? 2. What's n factorial divided by n plus 1 factorial? 1 over n plus 1. So I have an n plus 1 in the denominator. And this limit equals 0, less than 1. So the series converges. And the ratio test guarantees absolute convergence. That's a nice thing as well. So questions on that example? Couple of things that I just from the quiz we might need to remember how factorials and fractions with factorials work. Some of us made a few mistakes with the problem that had to do with factorials on the quiz. All right, let's look at another example, and then we'll talk about the root test. We're looking at the sum n equals 1 to infinity of 3 to the n over n squared. And we have these exponentials. That tells me that that the ratio test might work here. Is there another test that we might be able to use here? What's that? Direct comparison. What would we compare this with? 1 over. This is going to be larger term by term than 1 over n squared, right? Did you say direct comparison or limit comparison? So we couldn't use direct comparison because this is going to be larger term by term than 1 over n squared. Could we use limit comparison? Will that work? What's that? Or we could just use a ratio test. I just like to think about the different alternatives that we have and how we might approach it differently. All right, so let's use a ratio test. We have these exponentials, so let's use a ratio test. So we're going to look at the limit as n approaches infinity of 3 to the n plus 1 over n plus 1 squared times n squared over 3 to the n. And what does this simplify to? Three. Okay, we're off to a good start. What else is in the numerator? N squared. Okay, good. I think that's all that's in the numerator. In the denominator? N plus 1 squared. And what's that limit? 3. And what does that tell us? Diverges. So the series is going to diverge. I like pointing out at this point in this chapter that when a lot of times we tell math jokes, when I tell math jokes, and it has to do with not actually doing the problem, but knowing that a solution exists. It's similar to what we're doing here. We know that the series converges, so it has a sum. We don't know what the sum is. So we know a sum exists, but usually we can't figure out what it is. All we know is that a sum exists. So for this particular series that we just looked at here, It converges, but we don't know what the sum is. So we've shown that a sum exists, but we don't know what the sum is. So I like to make that little connection. We're kind of doing that here when we talk about series. All right. Any questions on the ratio test? Okay, let's talk about the root test. The root test is usually the stepchild of series tests. No, but does anybody like the root test? You never learned the root test? You never learned the root test? Okay. The root test. So, the sum a sub n is an infinite series. It can have positive, negative terms, just like we talked about in the ratio test. We have three conditions again, or three outcomes. Our series converges absolutely. And we just look at a limit again of the nth root of the absolute value of a sub n. And that needs to be less than 1. Our series is going to diverge if this limit is greater than 1. And no conclusion if the limit equals 1. This shouldn't be an exponent here, this should be a subscript. I wrote it right the first time. And if this equals 1, then there's no conclusion. And the root test, as you might guess, works well for series that involve nth powers of terms. So so if you have an nth power, if you have terms that involve nth powers, then the root test can be helpful. And it's very similar. The way we come up with this is very similar to what we did with the ratio test. This involves comparing our series to a geometric series, and that's where these conditions come from: less than 1, greater than 1, and equal to 1, because we end up comparing this to a geometric series. So I want to show you an example where I'm not going to go through this one, but this is an example of where the ratio test would work, but the root test saves a lot of work. So if we look at the sum, n equals 1 to infinity of e to the 2n over n to the n. We could use the ratio test here. But because we have this nth power, the root test is going to be nice because we just look for the limit as n approaches infinity of the nth root of e to the 2n over n to the n. And what is this limit? How does this simplify? E squared over n. So That's an easy test. Ratio test, much more difficult with this example. It's doable, but much more difficult. So this one not too bad, using the root test. Let's look at another one using the root test. This one a little more obvious. I think this one's a little more obvious. The next one maybe not quite so obvious. N equals 1 to the infinity of n squared over 2 to the n. Ratio test. Ratio test would work. But let's look at the root test. So we're going to look at the limit as n approaches infinity. I don't need to worry about an absolute value here. So we're looking at the nth root of n squared over 2 to the n. How can I rewrite this? Well, let's look at the denominator first. Let's do the easy one. What's this? 2. And I'm just going to rewrite the numerator as, I'll just leave it like this, nth root of n squared. I want to get to something that looks a little more familiar. So this equals, how can I rewrite the nth root of n squared? Let's go even more basic than that. What can I do with this exponent? What is it? Who said? Someone said something?
I did, but I don't.
Yep. What do we do with it?
Make it a fractional.
Isn't this the same as writing the nth root of n squared? Using our rules of exponents? Over 2. And what's the limit as n approaches infinity of nth root of n? We talked about that. This is a common one. Do we remember? 1. So this is 1/2. This limit's 1/2, less than 1. So this converges. So the root test can be helpful when you have nth powers in your terms. Questions? All right, I have some questions for you. So let me grab a couple of things here, and we'll take a look at what tests we might use on these series. Oops, I'm in the wrong chapter. So we want to look at these series, and we just want to talk about what tests we might use for each different series. We're not going to go through the test, but let's look at the series and decide what test we would use. So for number A, we have this series n plus 1 over 3 to the n, 3 times n plus 1. What test could we use here? Nth term. Okay, good. And the nth term, what do we know about the nth term? The limit as n approaches infinity of the nth term is 1/3, so that tells us diverge. So we're done. That was a 10-second problem. How about B? Someone said geometric. We have a number here, a number raised to a power. Pi over 6 greater than 1 or less than 1? Less than 1. Pi is a little bit bigger than 3. So this is going to be less than 1, so this is geometric. How about C? This one's a little trickier, but let me help you out here. Let's look at this and this. How are those two related? Someone said it? Integral test. We have the derivative out front here, and we have e to the u, and we have a du out front. So we might be able to apply the integral test here. We could integrate this fairly easily. How about D? Direct comparison to 1 over n? Is that going to help us? Term by term, how does this fraction compare to 1 over n? Smaller, right? So can we use, if our term by term is smaller than a divergent series, does that guarantee that we diverge?
Yes.
This one goes up here, this one can do whatever it wants down here. Well, what could we do with the harmonic series with this one?
They can be alternating series. No.
What's our other test that we can compare series with? Limit comparison. Do the limit comparison with the alternating series. And we've also talked about this is the general harmonic series. We've demonstrated, we've gone through the proof that diverges. So if you told me this is a general harmonic series, so it diverges, I would be okay with that because we have shown that diverges already. How about E? What would I do with this? This is an alternating series, so we'd use the alternating series test. How about F? Ratio. That's a good one for a ratio because of the factorial. G. Oh, look at this. This is a gift. Root test.
Yeah.
We have this nth power here. It's saying please use the root test. It's asking very nicely. All right. The integral test. If you're masochistic, you would choose the integral test for that one. All right. I have another set of questions for you. All right, let's focus, guys. All right, for these, we want to look at these. Come on, guys. We want to look at these and decide which of these series are the same. So for 69, we're looking at these three representations of this series and decide which two are the same. So what we're doing is looking at the indices and deciding which are the same. Who said it? A and C. So why are A and C the same? Right. So we could cancel this n plus 1. Or we could look term by term. This one starts at 1 and this one starts at 0. So if we go term by term, they're going to be the same. So this one is going to be A and C. How about number 70? B and C, right? This one's starting at n equals 4. So we're leaving off the first several terms. They don't want the first 4 terms. Maybe you could start a series. You could look at the series of 4 because we can delete a finite number of terms and still have convergence. So maybe the first 4 terms they don't like for some reason. How about 71? What's that? A and C? So look at the signs of the first terms. So if we look at A and C, the signs of the first terms are going to be different. So what does that leave? A and B. This one has to be A and B. All right, how about 72, the last one? Which of these two are the same? Look at the signs of the first term. A and B for this one. If we look at the signs of the first terms, these two are going to have different signed first terms. All right, homework. Let me just check my numbers. I can't read my writing. All right, there you go.